Welcome to this explainer. If you're an engineer or a research professional working right at the very edge of measurement capability, well, you already know the deal. The line between absolute success and complete failure often comes down to sub-microtesla fractions. It's wild, but it's true. So today, we're going to unpack a highly structured, honestly fascinating methodology for calibrating and designing high-precision optomechanical sensors, all using MATLAB. We're going to break down exactly how you can take raw, noisy hardware data and mathematically forge it into absolute precision. All right, here is our roadmap for today's deep dive. We'll start with the system basics, move through the actual MATLAB workflow, dig into the mathematical precision of the algorithms, compare some sensor performance metrics, and finally, look at system validation through frequency response and Simulink.
Let's kick things off with Section 1, Optomechanical System Calibration Basics.
So let's establish the problem space we're playing in. We are talking about the incredibly sensitive interplay between optical elements, think lasers and photonic cavities, and mechanical degrees of freedom, like microactuators or suspended mirrors. Because light is literally interacting with physical motion here, unparalleled calibration isn't just nice to have, it's absolutely crucial. Any tiny bit of noise, any microscopic error in that mechanical motion, and boom, it severely disrupts the light interaction and completely ruins your data.
Moving right along to Section 2, the MATLAB calibration methodology.
To tackle this massive calibration headache, the research lays out a really elegant four-step workflow built entirely within MATLAB. Step 1 is data acquisition, grabbing those raw accelerometer and magnetometer files and structuring them into clean MATLAB variables. Step 2 is sensor calibration, where that raw, messy data gets mathematically corrected. Step 3 zooms in on sensor design, letting engineers define specific structs for things like sensitivity and frequency range. And finally, Step 4 is visualization, which turns all that pure math into dynamic, readable plots. This entire sequence guarantees that your data is protected and refined from the second it leaves the hardware until it hits the engineer's screen.
Which brings us to Section 3, mathematical precision of algorithms. Now, uncalibrated magnetometer data is, frankly, a mess. To fix it, the MATLAB script analyzes those sensor readings and uses linear regression to fit a perfect mathematical sphere right over the scattered data points. By hammering out the coefficients A, B, C, and D, the algorithm mathematically locks in the sphere's exact center, its radius, and the residue. Think of this sphere as your highly rigorous, mathematically pure baseline for calibrating the rest of the sensor.
And the hard proof of that algorithm's accuracy? It's all in the output metrics. The system establishes the center point and calculates a radius of about 30.5 microteslas. But the real star of the show here, the number you should really care about, is the residue. It was validated at an incredibly low 0.0057253 microteslas. Actually, achieving a residue that low means the mathematical fit is virtually flawless, guaranteeing your aerospace or biomedical sensor is fundamentally reliable. The methodology even visualizes this dynamically using a really cool pebble rolling simulation to track movement intensity in real time.
Next up, Section 4, comparing sensitivity and noise.
When you're evaluating structural designs, you're going to see massive variances in sensitivity depending on the hardware. For instance, the accelerometer boasts a relatively huge sensitivity of 0.5 millivolts per G. Meanwhile, highly specialized sensors like force detection and torque magnetometry are orders of magnitude lower, sitting at 0.01 and 0.005 respectively. But as any research professional knows, in the world of high-precision engineering, sensitivity is only half the story.
And here is the other half, the noise trade-off. You really can't get high sensitivity without inviting in some interference. The accelerometer, despite being super sensitive, comes with the highest noise level at 0.1 millivolts. Conversely, that highly specialized torque magnetometry sensor, the one with the lowest sensitivity, minimizes noise down to a whisper-quiet 0.002 millivolts. Interpreting this trade-off is absolutely critical. You have to select the sensor profile that delivers the optimal signal-to-noise ratio for your exact operational environment.
Let's look at Section 5, Evaluating Frequency Response Visualizations.
We cannot overstate how important it is to visualize frequency response. By plotting these equations out, researchers can visually assess a sensor's dynamic range and spot trouble before it happens. Take the force detection sensor versus the torque magnetometry sensor, for example. The force sensor tracks sensitivity to external forces across a massive operating range, all the way up to 10,000 Hz. The torque sensor, which is tailored specifically for rotational forces, operates on a much tighter curve up to 5,000 Hz. These visualizations are what allow engineers to pinpoint exactly where frequency-dependent effects might start to degrade the signal and compromise data accuracy.
So this MATLAB methodology ultimately empowers engineers to define parameters optimized for completely different mechanical dynamics. Whether you're tracking standard motion under 2000 Hz or pushing the limits with high-frequency external forces up to 10,000 Hz, the software framework gives you the exact structural parameters needed to prototype your sensor accurately.
Finally, all of this theoretical design and mathematical calibration has to be brought to life. Bringing these designs into MATLAB Simulink lets the research team simulate actual physical interactions using translational simscape and optomechanical blocks. By generating simultaneous output graphs for force, voltage, and torque, engineers can validate that those rigid mathematical models actually hold up under dynamic, simulated real-world conditions. It's the ultimate sanity check, the final proof of concept, right before the expensive manufacturing phase begins.
It's truly mind-blowing to think about what this means for the future of engineering. When your software methodology can reliably achieve sub-microtesla precision and perfectly balanced frequency responses, you're not just iterating on existing sensors. You are completely expanding the definition of what is physically possible to measure. So, how will these hypersensitive systems push the boundaries of robotics, aerospace, and automation over the next decade? That is the exciting frontier this methodology opens up. Thanks for joining me on this explainer, and keep pushing the limits of what's possible.